Good morning. Good morning. I am so delighted to be able to introduce Josh Sugar to you this morning. Josh got his let's start with the bachelor's, master's, and PhD in material science at Berkeley. He postdoced at Sandia, California in the materials physics department, and he was converted to staff in 2010. In addition, well, he's still there. And in addition to his technical work, he is now managing the Sandia, California microscopy team. He is an expert in many things, including TEM, SEM, FIB, EDS, EOLs, EBSD, Nest doorbell installation, additive manufacturing, energy storage, and a lot of things I'm probably forgetting. And today he's going to talk to you about the thermal history of materials, the origin of Earth, civilization, and advanced manufacturing.
Thank you, Susie, for that kind introduction. Thank you all for attending today and your time. I really appreciate being able to speak to you today. It truly is an honor. So hopefully the title of my talk is a little bit exciting to you, and we'll get into that, and we'll talk about what that means in a moment. But first, I do need to thank my collaborators, because in science, none of us work alone as an island. It's a team effort, and we always have to mention the people that we work with, because it's very important to have a strong team behind you. And in particular, I just want to point out Thale Smith. He was a student at UC Davis, and he's now at Sandia as a postdoc, and working with him is great, and a lot of his work is represented here in this talk today. So when Susie asked me to come here and speak to you, I really wanted to talk about something that would connect the work we do at Sandia and the work you do here. And I thought about what would be a good way to connect these two institutions that, at least on the surface, seem to do things that are quite different. And as I looked at your website and looked at what the mission of this institution is, it talks about, gaining knowledge for the improvement of mankind. And one of the things that was being advertised on your website right now is a recent NASA astrobiology grant, and it talks about planet-wide transformations, the growth of the crust and the continents on Earth, and how and in what order were the ingredients for life on Earth manufactured and assembled. And so this language about the order of things being manufactured and assembled really got me thinking about things. And then I looked at what we do at Sandia, and it says Sandia develops advanced technologies to ensure global peace. And so we do a lot of work on material science where we're developing materials and manufacturing processes. And to me, the connection there is that when we develop these materials and manufacturing processes for our needs, it's all about the thermal history, meaning the time temperature profile of these materials, right? That's what I mean when I say thermal history. And we carefully tailor the thermal history of all the materials we study at Sandia and that end up going into our nuclear weapons stockpile to be something useful. But all of those materials that we use come from the Earth. So the raw materials come from the Earth. And what you work on here is that original thermal history, right? That very first thermal history that all materials saw. And so I want to make that connection to you and talk about thermal history and why it's so important in materials and how we use that to make materials useful in an engineering sense, which is what we do in Sandia. And so this is kind of the beginning, right? The original thermal history. There was the Big Bang and everything was hot, and all of you in this room know way more about this than anything that I could possibly say. The point of me showing this slide is just to make that point again, that the original thermal history of all materials that humans have access to came from this original thermal history and all these space bodies, that everything was hot, it cooled down over many, many, many years, right? And that set the distribution of the raw materials in the Earth, and that would define everything that we have access to as humans later, right? That it was this original thermal history that set everything. And it's unlikely that this particular thermal history actually was designed in such a way as to make materials as useful as they could be for engineering purposes. Right? That's one thing to think about. This probably didn't occur for that purpose. So then when humans came along, first we had the Stone Age, where humans could basically just pull things out of the ground and turn those things that they pulled out of the ground into tools that they could use. And that was kind of the first materials and the first tools that civilization used, right? But then we got smarter and we started, learning how to be smiths. We learned how to melt things down and how to forge things with our hammer. And this idea of a hammer and being able to, shape things, right? And pound things to change their properties is very, very important. Okay? And we started doing that with bronze first, and then iron, and then obviously things developed into more complicated metals. But all of these techniques that we used, where again, it was this thermal history. We heated and melted things, and then we could cast them, we could forge them, we would quench them, and those cycles of heating and quenching and pounding with the hammer changed the properties of those materials and made them useful. And that was how we got tools for farming, tools for medicine, tools for war, our culture and art, right? All of that depended on our ability to manipulate these materials, shape these materials, and control the properties of the materials. So, and the other point that I would make about these metallurgical developments is that very early on we did not understand why. We knew these things we had to do to make the properties better. We knew how to make a better samurai sword. We knew how to make Damascus steel, but we did not know why that made these materials better. So fast forward to today, and there's some sound here in this video. So what this is showing is a process that's very important to Sandia called high energy rate forging. So this is a forging process that we use, and there's only 2 places basically in the world that can do this kind of forging. Very fast, very high energy, high stress forging. Okay? And what you see is that the worker pulls this hot piece out of the furnace, puts it in the forge slams down, right? And that slamming down makes the properties of this steel very, very strong. And the time that it takes for him to then pull it from that forge and put it in the punch back is very important. It's crucial to the properties that you get from this material. And so we're interested in this because we need to make high pressure vessels, and we understand how this process changes the microstructure and makes the properties of the steel very strong so that it can hold gases at pressures higher than 10,000 psi. So sorry, I know that was loud. So that is a forging process, and then this is a conventional machining process with a 5-axis stage. So this is kind of, the modern technology for how you would shape something. So when you think about these manufacturing technologies, I want you to think about them in 2 steps. There's this initial step where we're making kind of a large chunk of material with a set properties, right? And that's that thermal history piece. Then we machine it and remove material to make the shape that's useful to us. So there's 2 steps, and this step does not typically change the properties of the material. Okay? So now, today, these new manufacturing technologies are coming online called additive manufacturing. And in additive manufacturing, you start with a 3D model of a part that you want to build. And a computer slices it into layers, and then you feed it into one of these machines, and then the machine prints the metal, much like an inkjet printer, right? 1 layer at a time. And so the left side here is this one technology called powder bed fusion, where you have basically a layer of powder, and the laser comes down and prints one of those layers, and you'll see that, kind of see that going on now, okay? And after it finishes that layer, it lets new powder on top, and this blade sweeps new powder across that bed, right, to put fresh powder there so that it can build the next layer. On the right side of the slide here, I'm showing you a process called directed energy deposition, where instead of having a bed of powder that's existing there already, you have powder shooting through nozzles into a laser. So the laser makes a molten pool, then there's powder shooting into that molten pool, and the table moves around so that you can print, one of those single layers. Then the head moves up and it prints the next layer. Okay? So these processes allow you to build 3D shapes 1 layer at a time. And what's important about these processes is that the shaping and making of the material is happening in one step simultaneously. So that has really changed how we think about manufacturing, because we no longer have this hammer, right? That's the point. We no longer have this hammer where we can shape these things. That's been taken away from us in a process like this, where these things are happening simultaneously. And so the question is, how do we get that hammer back? And that's kind of what I want to talk about. As we understand additive manufacturing, how are we going to get that hammer back? So these are two microstructures that I've always liked, the Widmanstätten microstructures from meteorites. I'm sure most of you are familiar with this. And the reason I put these microstructures up here is because they're, first of all, an iron-nickel alloy. And I'm going to be talking about steels, which are iron-nickel alloys. So that's another way we can connect. But also, the microstructure of these things, right, the shape of these pieces of the microstructure, the composition, right, what happens at the interfaces there, all of that tells you about the thermal history of the meteorite and tells you about the history of the universe. And many people in this room probably study that on these types of materials. And so what I am going to do now is, much like in this, the way you would pull apart the microstructure to understand its thermal history, we're going to pull apart the microstructure of these additive manufactured steels and understand their thermal history and figure out how we can get that hammer back. And so the questions that I am going to ask today and hopefully answer are, how does the unique thermal history of these processes develop microstructures in these materials? So what are all the features that actually make up the microstructure of these materials? How do each of these microstructural features contribute to the strength, right? Because it's different in a conventional material, how it contributes to the strength. How spatially uniform is that microstructure? Do we need to think about gradients and how these things are distributed? And then finally, how do we get our hammer back, right? What are we going to use as the new hammer to control these materials so that we can make things soft when they need to be soft, hard when they need to be hard, resistant to cracking when we want them to be resistant, deformable when we want them to deform? So here's an example of a microstructure of an additively manufactured stainless steel. So I might say things like 304 stainless steel or 316 stainless steel. They're all iron-nickel alloys with chromium in them, right? They're just different stainless steel, slightly different composition. And if you look at this, you see there's all different features going on here. There's dark things, there's medium gray things, there's light gray things. So let's look at each of these things and understand what they are. So first, if you look carefully, you can see these different layers of gray. And I've now outlined a particular feature with the white dotted line that I want to talk about. And that is the grain structure of these materials. So we know when you have a molten material and you let it solidify, right, little crystals form, and then those crystals grow, and then they impinge on one another, and that gives us the grain structure of the material. And we can actually measure that grain structure with a technique called electron backscatter diffraction, which I imagine some of you are familiar with, where you have an electron beam that scans across a surface, right? And at every position on that surface, you generate a diffraction pattern. That diffraction pattern will tell you the orientation of the crystal at the surface of this sample, right? And then you can map that orientation. And so these colored maps are showing you the orientation of these crystals at the surface. Now this image up here in the upper left, that is a conventionally manufactured material. So there were basically two plates of material that were welded together. And this giant round feature here with these elongated grains is a weld, right? That's the weld where these two plates were glued together. Now, if you look carefully at the sides of this image here where the base material is, and I blow that up, then this is what a normal grain structure looks like for a steel. You have this equiax structure with kind of roundish grains. But when you look at the welded material, you see these elongated grains where that elongation is happening along the direction of largest thermal gradient. So you have a molten material, and then the molten material solidifying from the hottest part to the coldest part of the material. And that's why you get a structure like this. Now notice the length scale here, where if this is a millimeter, right? So now in these additive manufactured materials, you're melting material layer by layer, a little bit at a time, and so it's very similar to a weld. So it makes sense for us to use the analogy of welding to understand how these materials form. And here's two examples. The other two images I have here are additively manufactured materials, steels, 304 stainless steels. And you can see these elongated grains that kind of change direction, right? And over in this one, you also see these elongated grains. And that elongation comes from the motion of the laser. And depending on how you scan that laser, it will change the grain structure, right? When the laser is scanning in and out of the page, you have one grain morphology. And when it's scanning left to right in the slide, you have a different morphology where that elongation is changing depending on which way the laser was scanning and melting the material. So we see that this grain structure that we have in the additive manufactured materials is very different than what we get in a conventional material. Yes?
Are we looking at in the plane of a layer or across the plane of different layers in this material?
We're looking at multiple layers. So in this one here, this is one of the layers. This is another layer. This is another layer. In this one here, we're also looking across the layers, but the laser was actually coming in and out of the page. Okay, and so you can't really see the side to side of it. But we are looking at multiple layers here. Thank you for the question. So the grain structure is very important and something we want to consider moving forward. So the next thing I want to talk about are these dark features here. And you see these dark features, these kind of stringy looking things, and they're distributed uniformly throughout the material. So what are those? Well, steel can have multiple phases and multiple crystal structures. There's a face-centered cubic structure, there's a body-centered cubic structure, and those are the main two that I'm going to talk about. There are others too, it turns out, but I'm not going to talk about those today. And when you have this molten steel, this complicated alloy that solidifies, you can have multiple phases form, as you would expect in a multi-component alloy. Right? And so this is an example of a phase diagram that's kind of a pseudo-binary, and it's showing you kind of how these things solidify. But the point I want to make is that if we can use that same technique, electron backscatter diffraction, and we can figure out when we have face-centered cubic material and body-centered cubic material, and we can map that out. And what we see is that we have this kind of fine-scale dispersion of this body-centered cubic material within the face-centered cubic material. Now, in these types of stainless steels I'm talking about, normally it all is face-centered cubic. So having this fine distribution of body-centered cubic is strange, is not normal. You do see it in a weld, but the length scale is very different, much like the scale of the elongated grains is different. In the additive manufactured material, everything is at a much finer length scale than what you get in a conventional weld. This is just to show you an example of a conventional material. All right, in what would the body-centered cubic inclusions look like? And you get these kind of big stringers, right? So you could imagine that when you have a big stringer like this, surrounded by a big bulk material that's face-centered cubic, this doesn't really change the properties much. But a fine distribution of body-centered cubic material like this could have an impact on the properties. So we need to think about that. The next thing, so I've identified now the ferrite and the grain boundaries. So the next thing I want to talk about is this structure here, where you kind of see these different scales of gray, and there's these blobby looking things in there. So when you have these complicated alloys solidifying, I think it's very common that, and you know this, that the composition of the liquid and the solid in equilibrium with each other are often different. So what that means is that when something is solidifying, the solid has one composition and the liquid is different, and so the solid can be rejecting one of those solute atoms to the liquid. Now, depending on the speed with which that solid-liquid interface front is moving, you can have kind of a different morphology of that interface, right? And so when it's a fast solidification of something, you can end up with these things called cells, or these columnar cells, right? And these cells are rejecting one of those solute atoms to that solid-liquid interface, and so you end up enriching a region of the material with one of those solute atoms. And it turns out, because of this rapid solidification process in these steels, we end up doing this and rejecting some of the solute atoms to the interface. And so you end up with these cells that are enriched in chromium. And here's an example in the SEM of doing a compositional map. And I'm showing you in green the chromium-enriched regions, which are these cells. It's interesting that these enriched regions also correspond where that ferrite is found, right? Those ferrite inclusions. And that's because ferrite is stabilized by these chromium-enriched regions. Now, and in the TEM, in the powder bed fusion material, you also can see this fine scale, same kind of solute segregation of chromium enrichment. Okay? So again, this is something, oh, and I should explain, so imagine we're looking down those columnar cells here, right? We're looking on them this way instead of them growing up and down like I showed you in the previous slide. So this, again, is something that you don't see in the conventional material, and it's something we need to think about if we're going to try and understand the strength of the material. Finally, the last thing now are these round things that they kind of look like pores, right? And you think they might be pores. The question is, are they pores? And the answer is they are not. They are actually oxide inclusions. And so if you think about a powder, right? This powder is just sitting out in air, or we try to keep it in a clean environment. But of course, it's a stainless steel. The surface is going to oxidize. It's very hard to keep oxygen out, right? So the surface of this powder has an oxide on it. Then we melt it, and that oxide gets into our material and makes these inclusions. And so you can see these dots here, and if we look in the TEM at the structure of these oxide inclusions, they can actually be quite complicated. So this particular oxide particle here, you see, has a region that's rich in silicon and oxygen. It has another region that's rich in sulfur. So there's sulfur and oxygen in the material dissolved, and it nucleates out and forms these particles, right? And that can actually be beneficial for two reasons. One, because these oxide particles can increase strength. I'm going to talk about that in a second. But also because it pulls the sulfur and oxygen out of solution of the stainless steel, out of the solid solution. And that can make steel more ductile, because sulfur and oxygen often contribute to steel embrittlement of steel. In one of the other materials here, we just saw simple chromium oxygen-rich inclusions. And when you look at fracture surfaces, you see these inclusions everywhere. So it's very clear that these inclusions are everywhere. And as I said, just to repeat again kind of how these things get there, you have these powder material where there's oxide on the surface or oxide included in the powder. It gets into the melt, right? At some point, that melt is cooling down, becomes super saturated with the oxygen, and you end up having a normal nucleation and growth problem, where these oxide inclusions will first nucleate, and then they'll grow as the material is still hot, right? And then they get distributed everywhere in the material. And then the laser passes over again, and you get some cyclic heating where these things could continue to grow a little bit more. And that's how you get the final size distribution of these oxide particles. And as I said, these oxide particles are typically not something that you get in a conventional material. And so it is important because they can actually alter the grain structure of this material after the cyclic heating. So here's an example of a traditional material where you don't have those oxide inclusions. But over here, where you do, you see the grain boundaries often get pinned by those oxide inclusions. So the thermal history of this material, as it melts and then solidifies and then gets cyclically heated as each layer is added to it, right, those grain boundaries move and can sometimes get pinned by these inclusions, which is important to understand as we're going to make sense of the full thermal history of this material. So we've identified now the importance of grain boundaries, cell boundaries, oxides, and ferrite in understanding the microstructure of this material. So the question is that everything? And of course, I'm asking that because the answer is it's not everything. So dislocations are something that at the length scale of that micrograph we can't see. Now, a dislocation is a kind of mistake in the atomic arrangement of these materials, right? So just, very fundamentally, you have a crystal and atoms are arranged in this periodic way. And when there's a mistake in the stacking of these atoms, you have something called a dislocation, which is right here in this image. And the deformation of materials, in particular metals, but all materials, depends on how dislocations move through these materials, right? And this GIF here is showing you what happens when you apply a shear stress to this metal, how the dislocation moves through by breaking one bond at a time, right? That's very important because it's the lowest energy configuration of how you can accommodate shear. And so here's a TEM image of some dislocations in a material. Here's an atomic resolution TEM image where you can see dislocations in these kind of darker regions, and those dislocations are making up a low-angle grain boundary. But dislocations are critical to understanding the deformation of the material because, as I said, how the dislocations can move through the material defines how easy it is for the material to deform, to bend, right? But also because all the other microstructural features I just mentioned, oxides, grain boundaries, ferrite, right? Even other dislocations, all of those will have the ability to change how dislocations move through the material. So when we talk about the fundamental strength of the material, we are talking about how do dislocations move through the material, which means how are they interacting with these other features that I just presented to you. So that's what we need to understand, how dislocations are interacting with all these other microstructural features in the material. So can we see the dislocations? Yes, we can. So here's an example of a forged material, and you can see there's so many dislocations. So if you go back and remember that slamming that I showed you, that high energy rate forging, you're introducing so many dislocations, and that's what makes that material so strong. In a conventional material, it is this working, right, and introducing dislocations that makes the material strong, because then when you try to deform it, those dislocations are what impinge one another. They all get tangled up, and that makes the material strong. And you can see there's so many dislocations you can almost not see through the material. All these black lines are dislocations. Now in the additive manufactured material, you can see these black lines here too, right? And so there is a dislocation structure here, and it does have a somewhat similar kind of look to it as the forged material. You can see there's kind of this regular spacing of the dislocations, and that's important. And the other thing is, I asked this question early on, are these things distributed uniformly in the material? And it turns out that if you look near the base of the material, so if you imagine this tower is something we built in that machine, so the base is down here on the base plate or the substrate, and then we've built up this tower here, right? So near the base, we see more dislocations than we do near the top. So that's going to have implications on the strength of the material and how uniformly distributed the strength is. And we need to understand that. So now we've talked about all the different microstructural features that are present. And we've picked apart this image, and I've even shown you things that you can't see in this image. So as I said, the next question is, so how does each of these features contribute to the strength of the material? That's ultimately what we want to understand. So the grain boundaries are an important strengthening mechanism that people talk about all the time. And there is a mathematical relationship that relates the strength of the material to the grain size. Because when grains get small, as the dislocations are moving, they hit more grain boundaries, and it makes it harder to move them, so the material is stronger. So here's an example of the grain structure at different locations in a build, and we can see the grain size does change slightly. And if we calculate what we expect that change in strength to be based on that change in grain size, it's about 3 to 9 MPa. That's not a very big difference. That's fairly small. So it's unlikely that grain boundaries are playing a big role as a strengthening mechanism in these materials. So I also talked about the ferrite and the compositional microsegregation, right? And if we just think about the compositional microsegregation, so where that chromium enrichment region is, and again, we can calculate the strengthening that's due to this compositional difference that happens on this kind of micron length scale. And we can look at how the compositional segregation length scale changes from the bottom of a build to the top of a build, and calculate what we expect that difference in strength to be, and it's 9 to 12 MPa. So this is clearly a bigger effect than what you get from the grains, okay? It's still not a huge effect, but it's a bigger effect than what you get from the grain size. Now I talked about the oxides too as being something that can strengthen, and there are things called oxide dispersion strengthened steels. So that's something where when you have a fine distribution of these oxides distributed uniformly in a steel, those oxides can prevent dislocation motion and strengthen a material. And so I said there's these oxides everywhere in the material, and we can calculate again the strengthening that we affect from the oxides here. And there is a difference between the size of the oxides as we look at different locations in the material. And so the question is, how much do these strengthen? And it's 6 to 8 MPa. So it's not a very large effect. So it looks like the compositional segregation has a bigger effect than both the oxides and the grain size. Now what about dislocations? So let's talk about dislocations a second. Now, we said that dislocations contribute to strengthen a material. In a conventional material, dislocations are one of the main strengthening mechanisms. And so here's an example of a conventional forged material, right? So you imagine that forging I showed you before, we slam something down. And so what we have here is a plot of hardness versus dislocation density. And as we anneal something, we can actually recrystallize the material and get dislocations out of it, right? That's what happens. And so this here is square root of dislocation density, and as dislocation density is decreasing, the hardness is decreasing. So this explains the strength of a conventional material, right? The more dislocations you get, the more they interact, the stronger the material. And this is an example of a technique where you can measure the dislocation density. And what you see here is that when you anneal at a low temperature, you still have all the dislocation density. So this bar here is showing you the magnitude of the dislocation density. So white and yellow means more dislocations, and dark means less. So as we anneal this material, you can see that these grains are recrystallizing and reforming, right? And as they're doing so with less dislocations, with none of these atomic stacking defects in the material. So you end up making a softer material where dislocations can move much more easily, okay? And the material is softer until eventually you've gotten rid of almost all the dislocations and now the material is very soft. So what I'd like to do is specifically talk about this technique here where we're measuring dislocations, because this is an advanced microscopy technique that we've been working on. So I just want to divert to that topic just for a slide or two here to explain why I think this is important, where this comes from. So clearly it's very important to quantify the dislocation density in these materials because it affects the strength. And so if we think about the total number of dislocations that are in a material, there's going to be statistically stored dislocations as part of it, and then something called geometrically necessary dislocations. And with this technique, electron backscatter diffraction, it turns out you can actually measure those geometrically necessary dislocations. So how do we do that? So if you imagine crystallographic planes with a slight misorientation between them, and I told you that this EBSD technique is measuring the orientation of those planes. So imagine you're scanning the electron beam across this image, and there's this slight change in orientation of those crystallographic planes. You ask yourself, well, how is this small misorientation accommodated? Well, it's accommodated by these dislocations, geometrically necessary dislocations. And so you imagine you have a large number of dislocations here. If those dislocations are opposite sign, right, because these dislocations can actually have a sign to them, depending on how they're oriented in the crystal, then they cancel each other out. And if they cancel each other out, then there is no change in misorientation across this thing here. But when you have these green ones, which are unmatched or unpaired dislocations, then you do have a change in orientation that you measure. And that change in orientation, theta, can actually then be used to directly calculate a dislocation density of how, knowing the crystal structure of the material, right, how many of those dislocations do you need to accommodate that misorientation. And in that way, we can map the dislocation density. And if you look carefully at these maps here of dislocation density, you can actually see the individual melt pools from those laser scans. So if you look, you can see like right here, it might be easier on this dark one. You can see you kind of have one amount of dislocation density, maybe a little bit lower, kind of where it solidified last, or first, excuse me, and then it kind of gets higher when you go to where it solidified last. So as it's solidifying, it's kind of constraining itself, and then the last bit to solidify gets strained the most and forms a lot of dislocations. Now, it's also possible to actually do this with such a resolution where you can make out individual dislocations. And I just point this out to show kind of the advancement of microscopy. So here's an example where you can see these individual dislocations right here in this particular image. Was basically a TEM image, and you can see individual dislocations. And if you use a small enough pixel size when you're measuring this, and a technique called transmission Kikuchi diffraction, which is the same as EBSD, but instead of diffracting and using backscattered electrons from the surface, you're going through the sample. Other than that, though, the technique is essentially the same. So you can transmit electrons through the sample, measure the diffraction pattern, measure changes in orientation, and again, map out dislocations. And you can map out individual dislocations and misorientations in the material. So I just want to point this out as this is an important technique that we've been using to actually quantify dislocation density. And the reason that's important is, one, because it's quantitative. Where in the TEM, it's very hard to quantify dislocation densities because you just have these black squiggles. But also, in terms of the sample area you can actually analyze, in the TEM, one of the limitations is you're always analyzing a very small area. And because the scale of these structures is so large, we really need to map out atomic scale defects in a very large area. So we need a technique like this where we can map out dislocations over large areas to understand the gradients in the dislocation density of these structures. So now we go back and look at our material, and we can look at how dislocations affect the strength of this material, because we can quantify it very carefully with this technique I just discussed. And if we look at the top and the bottom of one of these builds, we kind of see a large difference in dislocation density using this technique, where we have, 4.3 times 10 to the 13th dislocations per meter squared here, 3.4 here. We can use, again, our mathematical relationship, and we see the largest effect of strengthening with dislocations, 21 to 25 MPa. This plot here is actually a histogram of all of the dislocation densities in the entire image. And so you see that in the top, it's shifted to lower dislocation densities. So it's showing the same thing as this average. I'm just showing you the full distribution of dislocation densities in these images. So now we talked about how as you anneal this material, right, which is important to understanding the thermal history, when you anneal conventional material, you reduce the dislocation density, the material gets softer. So what about in additive manufactured materials? Because we're going to melt it and solidify it, and then it's going to be heated again and again as each layer is added. So what does that do to the dislocation density? So this black line here is that same curve of dislocation density versus hardness for that forged material. And we see that the strength drops, right, as the dislocation density decreases during annealing. In the additive manufactured material, we see very different behavior, where initially you have this dislocation density that doesn't change, but the material is getting softer. Okay? Eventually, at long annealing times and temperatures, the behavior approaches the same as what you get in the conventional forged material. Okay? That's here. But these initial anneals have this very strange behavior. Correct. So we can get, that's right. And that's one of the points I want to make, that with this laser process, we can make high strength material. It's not all weak. It is possible when your process is dialed in correctly that you can make a very high strength material. So these are all steels, and so it's possible to do that. I'm about to talk about that, but certainly it has a lot to do with the dislocation density and the thermomechanical history. So the fact that you have material that's solidified, then you have molten material that then solidifies very rapidly, there's a strain put on every single spot that solidifies, and that introduces dislocations that makes it stronger. So this idea of a constraint and a melt and solidification is important and does make it strong. Just going back to this now, at the long annealing times and long annealing temperatures, we see the same sort of behavior that we see in the forging, where we can recrystallize material and create new material with lower dislocation densities. But what is happening here, which is related to this question I was just asked, so what is happening here where we're making strong material, the dislocation density is not changing, but the strength is. And if we look at micrographs of what happens there, what you see is that this compositional microsegregation appears to be going away. So that compositional microsegregation, which was one of the other largest strengthening effects that we looked at, appears to be going away. And why is it going away? Well, it's just a diffusional process, right? And we can think about it and do some root DT, simple calculations. And for different times and temperatures, if we calculate what we think it's going to take to homogenize out that compositional microsegregation, then in fact, it matches up with what we expect. And so what you see is that at these lower temperatures, removing that compositional microsegregation does help dislocations be able to move and softens the material without changing the dislocation structure. So this compositional microsegregation is very important to the strength. So if we think about now the overall strengthening of this material and how do we think about all the different microstructural effects of this strengthening, we can think about this red curve as being the forged material, where all the strength essentially is coming from adding dislocations to the material. So we have dislocation density, and all the strength comes from dislocations. Whereas in the additive manufactured material, it's different. We have some other effects here that I didn't talk about so much, but the two main microstructural features to consider are the dislocations and the microsegregation. Those two things make a big difference in the strength, and that's very different from how we think about a conventional material. So, now, let's talk about the strength a little bit, what the strength actually is, and is it as good as a regular conventional material, and also about these gradients. So I talked about how uniform are the properties, right? So here's two different builds. So here's an example where we built a rectilinear block basically laying down on the plate. And then these white things here are tensile bars. So basically we took this block, machined out those bars, then we pull on them with a stress-strain curve, a stress-strain machine, right? And we look at when they break. So we're measuring the deformation and then when they break. And then this here is a tall tower that was built where we did the same experiment, but now we had this tall tower. So the material that was tested here experienced a slightly different thermal history than the material here, because here it was it had a lot of contact area with the base plate, so the way heat moved through the material was different compared to here. And what you see are two different stress-strain curves, right? And these stress-strain curves tell us what the yield strength is, which is typically what I'm talking about when I'm talking about strength. And the yield strength had a 22% difference, so that's important. That's a quantifiable difference. It tells us it does matter the way that you build these things in the thermal history. That's going to affect the properties, right? The ductility is also different too, but I'm not going to talk about that too much. Now you might say, well, Josh, that's simple. That's just an orientation effect. You built one flat, you built one straight up and down, the layers are going this particular way, so you're just pulling apart the layers, right? That's why it's so much weaker in that direction. And I would say, no, that's not true, because we did this experiment where now we built a tall tower but had samples running this way and this way, where the region that was tested actually all had a similar thermomechanical history, and the strength was only 2% different. So it was very similar. Now, hardness is another way to measure these changes in strength, and I show you this just to show you that we've measured this in other ways and see the same effect. We always see that the strength is higher close to the base plate. There's something going on near the base plate where the material is always harder and stronger there, right? And the other thing to remember is that every single point in these builds has a unique thermal history, right? Because every layer you build changes the thermal history of the thing before. So there's no point that has the same exact thermal history, and it all depends how you scan the laser and how you build these parts. You can build one thing multiple ways. So we know that the properties are different, and we know that the thermal history is very complex, and every point has a different thermal history. Right? And here's an example showing you time, and if you look at different locations, you see this oscillatory behavior. There's all these different thermal histories, right? So how can we understand these unique thermal histories? How can we use them to our advantage, right? And eventually what we want to do is get that hammer back. So how are we going to use this kind of thing we're talking about here to get that hammer back? And the answer is we're going to do it with a computer, and with an understanding of our multiphysics models so that we can predict what the best thermal history is for a particular shape. So here's an example of a multiphysics model that we've generated at Sandia. And what we have here is a thermal camera where we are watching the build of a cylinder. And then in the computer, we actually have a heat source where we activate material, and we can actually build a cylinder in the computer. And what we can do is we can do a thermal and mechanical analysis on this cylinder as we build it, and look at where are the highest strains in this material. So I talked about how, the base plate is always stronger. The base plate is this large constraint. Material is solidified and being constrained by that base plate. It's strained higher near the base plate. You get more dislocations there, and it's stronger there. And so we can predict that with our computer models. And so here's an example, just again, comparing the experiment and the simulation, where you have these experimental images from a thermal camera watching the build of this cylinder, right, where it was kind of built in this spiral out pattern. And then in the computer, we also have the simulation where they kind of pick times where they showed you, hey, look, our thermal history, it looks like we're getting it right. It looks like thermal history that we see in the computer is similar to what we see in the experiment. And so here's what it looks like in the computer when they section it. And what you see is that there is this cyclic oscillatory behavior in the strain, right? So the strain means that as it's solidifying, it's being constrained by the surrounding material. It's shrinking as it's solidifying, and you're generating dislocations there. Anywhere where it's red, you would expect there to be more dislocations, and it should be harder and have a higher strength. So the modeling shows that this is going on as we build this thing. And so the question is, do we see that? Is that really what's happening here? And the answer is actually yes. So if we look at this thin wall build where we built these multiple layers, here's a EBSD showing you the grain structure, and here's a dislocation density map. And if you look, so this is a line averaged, the kind of line averaged profile of that dislocation density map, you see this oscillatory behavior, right? And that oscillatory behavior is that same kind of dislocation density oscillatory behavior in the model, where every time you lay material down, it's being constrained by the previously deposited layer, and you're generating dislocations, right, because of that shrinkage and constraint of the surrounding material. And it turns out that we can control this. So if we pick two different thermal histories to make this cylinder, we have one here where we did a spiral out to make a cylinder, and one here where we did a spiral in. So these are actually two very different thermal histories of this cylinder. And if you look at what you get in the experiment for where we expect the higher strains to be, the higher stresses, the higher dislocation densities, whatever you want to call this red region, then you see that you get these two lobes in the experiment, and the simulation also shows two lobes of this kind of red area, this high strain area. In the spiral in case, what you see is a higher strain in the middle. And that's what you see also in the simulation. So it turns out that, in fact, using the computer model to predict what the thermal history will be, we can predict what the strains will be so that we can understand the property distribution in these materials, right? The computer is our new hammer, because by changing the thermal history, we can control where the material's soft, where the material's hard, right? By changing these strains. So that's pretty much the end of what I had to say here. We talked in detail about the microstructural features in these additive manufactured materials, and we talked about how each one of these microstructural features contribute to the strength, and how we can use our computer models and our physical understanding of these phenomena to get our hammer back and control where these materials are strong, where these materials are soft, where these materials are weak, how we can control how cracks grow in these materials by changing the thermal history and choosing where there's going to be these red regions and blue regions, right? And then we can control the structure and property distribution in a full 3D part made with these new manufacturing technologies. So thank you very much, and I would be happy to answer any questions.
Very interesting talk. In terms of this last section, when you were discussing dialing in, making the hammer by dialing in the thermal, that was all about the dislocations, right? But you showed earlier that the hardest material you got was due to the compositional segregation.
Yes, that's right.
So are you doing that as well, finding a way to control that better?
So the compositional microsegregation is not something that's included in the thermal models, but it does affect how the dislocations are generated and how they move. So we know that it's important to the overall strength of the material, but we're not actually necessarily controlling it, as you said.
Right.
Yeah. So you're right. It is all dislocations right now.
So it's really there's lots of similarity to what we do in terms of like quenching, and I do experiments, and one of the things when you talk about thermal histories and you're talking about annealing process changes the temperature and durations, and do you also control the quench rate?
We have. It's very hard for us to control that, but we have done experiments with that a little bit, where you quench into a brine bath versus quenching in air or something like that. So
In the old days, our labs together high quench rate.
yes,
Dump stuff into the mercury.
right. Yes, mercury. Yes. Yeah. Yeah.
Yeah, so I thought the whole point of steel was the additives to it. I mean, otherwise you would just have like soft iron if you were. So I mean, even like pure iron would have dislocations, but it's not a very hard or strong material. The other thing is that maybe you said it, but it wasn't. It didn't strike me. I mean, did you make like a good definition of what hardness and strength were? I mean, it seems to me those things depend on things like strain rate and things like that. So I mean, something might be strong at one strain rate and weak at another strain rate or something like this. So how does that related? So those are really two different questions. How is that related to the microstructure?
Okay, so so in terms of the steel and the additives, yes, you're right. So steel was developed to have these higher strengths. You do have dislocations in any material, but because of the composition of steel and all the development over all the years and everything, it's a very high strength material, right? But the strength of all the materials is still governed by the dislocations and how they move through the material. And you change the energy of the bonding and how dislocations can move by adding those additives. So that's part of what makes steel what it is, right? So, The
Second question was, definitions of strength,
right,
strain rate.
right. So, yeah, and so I didn't really talk about strain rate very much. Strain rate is important, and things change, and you can have something called dynamic strain aging if you go to different temperatures and different strain rates as well, where as you stretch the material, it can recover and then do something else, and you end up with these oscillations in the stress-strain curve, right, where additives and dislocations are kind of interacting with each other while you're doing the experiment in a very dynamic sense. Here, everything we've done is kind of more like an equilibrium kind of experiment, where we're just trying to understand the fundamental base property of the material. So we're pulling at a kind of a slower strain rate just to get the baseline, because you make this material and you don't even know, what is it? Is it like conventional forged steel? Is it like a weld? Is it like soft iron? Right? You just don't know. And so, yeah, everything here has been kind of slow strain rates, but you're right in that the way these materials behave at different strain rates depends and isn't always the same as what you might expect. And those are ongoing studies.
I have a related question. If you plot these added materials or stainless steel added together on a strength hardness plot, does it plot very near the regular forged?
So like a conventional and an additive?
Yeah.
Yeah, and I had a plot like that before, but it turns out that and this goes back to your question too. It turns out that yes, they can lay right on top of one another. So for a forged material and an additive material, you can get a stress-strain curve where they're essentially on top of one another, but you do need to control the processes very well, and it depends on whether you've built it vertically and horizontally and where the constraints were on that particular thing. So, you might build a whole bunch of these tensile bars, and one of them will lay on top of the forged, another one will look a little different, another one will be up, another one will be down, right? Because the thermal history is different for all of those things. But the main point is, yes, what we found is that these materials, when you have 100% dense material, you can have material that's very similar to a conventionally made forged material.
And at Sandia, are you trying to reach higher strengths and hardnesses using in steel? Say using different compositions that wouldn't work well in forging, but maybe would work well with additive manufacturing.
Well, so let me answer that. The second part's a little tricky, but let me answer the first part first. So at Sandia, we care about these high-strength austenitic stainless steels because of their hydrogen compatibility, and we care about the storage of hydrogen at high pressures. That was one of the things I said early. So, so it turns out these austenitic stainless steels, that's just one of their strengths. That's what they're really good at, right? They are very resistant to hydrogen embrittlement, which there are some steel alloys that are very bad, and they touch hydrogen and they just fall apart. So so our interest in these high-strength steels is for hydrogen, and one of our fundamental questions we're trying to answer is, can additive manufactured materials be as good as conventionally forged materials? Because conventional forged materials are great. The additive manufactured materials, maybe not so much because of these complicated microstructures, where you have more than just dislocations going on. So the last part of your question, I think, is reversed a little bit, where we know conventional is good. The question is it worth investing in trying to make AM good as well when you have all these solidification features that you can't really get rid of?
May I? Yeah, so thanks. Thanks for the great talk. You touched on how rapid cooling can reduce the size of grains. And in the last part of your talk, you're describing how the strain is responsible for the grain boundary, or dislocation content. But it seems like, from what you were showing earlier with the dislocation density being higher near the base plate, that's also where you would expect most rapid thermal diffusion.
That's right.
And it seems like, that is like an engineering parameter that you could easily take advantage of by cooling the base plate, or even doing this in a cold room, so that you could, engineer smaller microstructure to, get the hardening that you desire.
So you're absolutely right. The base plate is critical, and that is where you have the fastest thermal diffusion. And what happens is, when you start a build, that base plate is cold. So at the base plate, you have one set of behavior, and then as you build the part, the whole entire system heats up. And that whole thing is radiating heat the whole time, and everything gets hot. And so near the top, when you're building the stuff at the top, it's built at a very different temperature than what was built before, which explains a lot of why we see these differences at the top and the bottom. And so you're right, you could cool it if you wanted to make it faster. That will make something called residual stresses much worse, right? So when you build this stuff and there is this rapid kind of cooling, what ends up happening is you cut this part off the base plate, and then it distorts itself because there's all this stress kind of that it's still holding on to. So we've heated up the base plate before to try and stop some of that, right? So you can also start everything at a higher temperature. But you're absolutely right. In terms of controlling where the strong and weak points of this structure are, that's exactly how you want to do it. You want to control the base plate. You want to control the temperature of each layer as you're building one layer on top of itself. Yeah, for example, but you have to remember that then you're adding heat, so each layer you have to wait and let things cool back down again. So it's going to make your process less efficient. But you're right, you could do something like that.
I guess I was entirely clear what the point of the 3D 3D manufacturing is? Is it because it's clear you're not making things that are dramatically stronger than you can do with forging. So is it the fact that you can make things that are in 3 dimensions that you cannot machine?
Correct.
But then you can only make small things because you're saying that if you have these large thermal gradients, there's going to have some big changes in strength from top to bottom, and if you make large structures.
So let me answer that question a few different ways. So one thing is, in a subtractive machining process, you make a big billet and then you remove most of it, right? So that wastes material. And we want to try to be as efficient as we can with the raw materials that we pull out of the earth. So one idea is that, well, with additive, you could be more efficient because you're not wasting material. Any powder that doesn't get melted and incorporated into your part, you could potentially reuse, right? So efficiency is one reason. Another reason is that you can make shapes with included voids and things like that you could never do and get to with a conventional machining process. So that's right. In terms of size, you're right. These thermal gradients do need to be considered, but there are people with big machines where people walk into, right, and build things. So Oak Ridge, for example, has built like a full car frame or something with additive manufacturing. So people are talking about wanting to do this, but I totally agree with you. I think you're right. You know, you have to ask yourself, what is the reason why we would build something we know how to build conventionally with AM? You're right, you don't. You want to look for the new shapes and the things that you can't do conventionally, or the things that are very expensive conventionally, and do that with AM. And I think right now, the question is, what are those things? What are those things that engineers are dreaming up and can't do? And can we use this technology to do that? And you're absolutely right. I mean, it's hard for engineers to get out of the normal day-to-day thinking and CAD design that they do, right? So I think we're at a place where this is changing. And what I was talking to earlier to Zach about was, you know, you could imagine that when Home Depot gets these machines, everybody will be at home coming up with 3D shapes that they want to build for their sink or their shower head or whatever, and we're going to kind of crowdsource engineering design, right? Because you don't need all these expensive machines to make things anymore. Right, you just want to make one. Right, that's right. And also repair is another thing. You can repair things with this that you couldn't do conventionally. Because you can imagine with the nozzle technology, say you have like a turbine blade where the edge is worn away or something. You can just add material there.
Any other questions? Well, I have one, but I'll ask you at lunch.
Okay.
Because I think we're all hungry. So let's thank Josh one more time.
Thank you very much. Thank you for your attention.
And please join us for lunch if you'd like.